So this video's purpose is to jumpstart you into Project 4. My understanding is that you haven't had a background in assembly language programming. You're still probably going to need to read all the Chapter 4 documentation, so don't expect this to be a substitute. So why this presentation? Well, we're trying to do the hardware definition language projects 1, 2, 3, and 5. Project 4 is really a design document. It's disguised as teaching you some machine language, but it's really describing how we're going to hook the chips together that we've built so far. We're starting this from the computer hardware, working towards the software. This course also supports working backwards through it. This is the more traditional computer science, starting with the software and then working down into the hardware. And these are basically outlines of the future courses you're going to take. The computer architecture is a class at both College Park and UMBC. Project 6 is about assembler also, but it's got a different objective. You're not learning assembler to discuss design of computer architecture. You're using assembler to begin building higher level languages, operating systems, virtual machines. So what have we done so far? Project 1 was building all these simple gates. The most complex of these were the muxes. We had to learn to mux the mux. Then we had these combinational chips. These are more equivalent to Chapter 5 in the book. And then Project 3 was about these sequential chips, which are much more like our flip-flops. They actually use flip-flops. They're clocked. This is Project 5. So you don't see Project 4 in here anywhere. Project 5 is basically how we're going to use these chips we've created so far to build the computer architecture. We have to have a discussion about the instructions we're going to send our CPU. We have to design those instructions, so that's what this lecture is about. So these are the actual chips that we've designed so far. Well, we haven't designed the ones in red, and we didn't design the ones here in purple. Those were fundamental ones given to us. The blue ones are the only 4 that we're going to use when we build our computer and CPU. So this is a picture of all the chips. The program counter is a register. RAM is RAM. ROM is also called RAM. It's just crippled RAM. We don't use the in or the load. Read-only memory never loads. There's never any input. So it's really a subset of RAM. So we can use a RAM chip to build a ROM chip. A register is another register, just like the program counter, and the D register is another register. This is the really simple mux. This A bit comes from the instruction design we're going to talk about coming up. And this is the arithmetic logic unit we've already designed. This is the really complex chip. So let's talk about what is an instruction. Okay, so where are these instructions stored? Well, the design is to store them permanently in this read-only memory where they can't be changed. So what do these instructions do? Well, they turn on these registers. They enable them. They cause them to load. They cause them to add, increment. They select one of these lines, A or M, going through the mux to feed it in here to the arithmetic logic unit. So they're basically playing with the control lines. Like the reset right here, they're going to control. Increment, they're going to control. Load, they're going to. Where are the instructions executed? Well, the question, where are they executed, is not a good question. They're stored here, and they turn off and on all these other chips. So when are the instructions executed? Well, they're executed on a clock pulse. Now, the things that are sensitive to a clock pulse are the registers, the program counter, A register, D register, and our RAM and our ROM. So where does the output of the ALU go? It goes into the D register. Where does the output of our ROMs go? Well, they go into those load lines, increment lines, and reset lines. So how do these chips turn into a computer? Well, the bottom part of this RAM, like the very bottom address right here, is connected to the keyboard. And then just above it, there's this block of RAM that's associated with the screen. The nandtetris assumes an 8K memory screen, so there's 8K pixels on the screen. And then this is just regular
memory where you put variables, the contents of variables. So the screen's memory mapped and the keyboard instructions are stored. And that makes it a full-blown computer. So how are we going to test and hook these all up? Well, we're not going to do that in this chapter. What we're going to do is we're going to look at software that's already hooked them up together and play with that software just to get an idea of what all the design issues are. Now the software that we're going to play with is called CPU emulator. This is the screen of its output. And I've got a 10-minute video that you might want to stop now and look at that describes this CPU emulator's operation. It's actually much easier to start here to understand computer instructions than it is to follow the rest of this video. So I encourage you to stop now and to watch this video. So what's the difference between an assembly language and a machine language? Well, this is an assembly language instruction. I've got it linked up. It's a sum.asm, not program.asm. Now, what happens is, this is what you type in, this is what you think. You think and program in terms of assembly language. And then you run it through an assembler, and what it does is turns it into binary code. 16 ones and zeros for each instruction. So the design of that we're studying is how these 16 bits are used, what each one of these zeros and ones means. Now when a program is assembled, the comment here disappears, the word sum disappears, the I right here disappears, the word loop disappears. So all the labels, all the human-friendly stuff disappears, and they turn into numbers. So this gets pretty hard to look at once you're inside the CPU emulator. This is called an ASM file. This is called a hack file. In order to test your ASM, you have to have a hack file created. Although you can load the ASM directly into the CPU emulator. So the assembly language is designed to put a human touch on top of these ones and zeros. So we have a chance of understanding what they mean. And we can speak of them in terms of mnemonics like greater than, or D minus A, or this is the spot in RAM that I want to play with right now, or this is a constant I want to subtract. Very few engineers actually learn to read binary. Although some do. I mean, if you stare at this stuff long enough, you start seeing this. Your brain can organize itself that way. So what is the nandtetris design philosophy? Its overall design philosophy is keep it simple, stupid. Do as little in hardware as possible, so it's almost a RISC, reduced instruction set machine. Keep the lower level languages as simple as possible. Machine language is low level. Assembly language is just a little bit. So how are nandtetris computer instructions designed? Here we see the binary version of this. So I has been turned into 1, 2, 4, 6, 16. So I has been turned into 16. Then this is an instruction. You can tell because it begins with a 1. This is a place. This is an address. So it begins with a 0. Then we have an instruction that begins with a 1. Then we have a place. Then we have an instruction, that's this one. Then we go to 100. 100 is what? 64 plus 32 plus 4. Yeah. So that's 100. They basically are alternating. We have a value that begins with a 0 right here. And then we have an instruction here that begins with a 1. Actually, it begins with 3 ones. They all begin with 3 ones. And then the next bit after this 1 is a bit that tells a mux whether to send the contents of the A register or the contents of RAM memory location into the ALU. The next 6 bits tell the ALU what to do. And we're going to look at those instructions coming up. The next 3 bits are destination. On the instructions, we either have the 3 zeros here, or on the instruction we have the 3 zeros here. Of these last 6, a group of 3 of them are going to be 0 in an instruction at all times. The next 3 are the destination, and then the final 3 are the greater than, equal than, or less than jump decisions. So this is an instruction, and that's an instruction. This is an instruction. So instructions can have an equal sign in them, or instructions can have a semicolon in them.
So we're going to go through the A bits, the C bits, the D bits, and the J bits, and then we're going to summarize. The A bit basically goes into the MUX and selects either the A register's contents or whichever RAM 16-bit address has been activated by the A register. The MUX then feeds this into part of the arithmetic logic unit, and then the D register's contents are fed into the arithmetic logic unit. So the A bit's basically selecting between A and M coming in. The C bits, well, if A is a 0, it's basically saying A is going to go into the arithmetic logic unit. That means A is treated as a constant. If A is a 1, then M is going to go into the arithmetic logic unit. M is that RAM location's contents. And then there's all these things we can do with the output of the ALU. We can force it to be a 0 or a 1 or a -1. We can just copy the contents of D right through the ALU, or the contents of A through the ALU, or the contents of M right through the ALU. We can not the contents. We can make them negative. We can increment, decrement, add D plus A or D plus M. So there's a rough parallel between these two. Now most of the time, this is on the right-hand side of an equal sign, and then the left-hand side of the equal sign tells us where to put these results. The D bits tell us where to put these results. There's 3 D bits, so there's 8 possibilities. We can put the results in both M and D, or all 3 of them, A, M, and D. So it's this side that determines where they're put, and this is telling the ALU what to do. Now the J bits are the jump instructions. And here on the left-hand side of, not an equal sign, but of a semicolon, on the left-hand side of the equal sign we have the instructions to the ALU. And then the output of the ALU is looked at by the jump instruction and compared to 0. So here the output of this instruction to the ALU is checked to see whether it's greater than 0. And if that's true, then it jumps. If it's true, then it loads the contents of the A register into the PC register. So really the jump instruction is manipulating the program counter. If it's false, it just goes to the next instruction. So it just increments the program counter as is normal. So this is our instruction summary. We have 3 1s no matter what on an instruction. Remember, if it begins with a 0, then it's a address. But if it begins with 3 1s, it's a computer instruction. A determines what goes into the ALU. C1, C6 are instructions to the ALU. D1 through D3 determine the destination of the output of the ALU. And J1, J2, J3 look at the output of the ALU and determine where to jump to. That's it.